Saxon Advanced Mathematics, Lesson 40. Greetings, students. John's going to start out with a little wordplay. He wants to talk to us about the word argument. He makes the point that this is a word that we're familiar with in everyday usage, but it's also used in mathematics with a slightly more specialized explanation. And he goes to a huge amount of detail. But what he basically concludes is that when we say argument, what we mean is the values input to a function. So if we say y equals the sine of x, then x is the argument. If we say f of x equals the cosine of 2x minus pi, this is the argument. If we say then this is the function, okay? So the function is just kind of the argument rather, is kind of the function itself. It's where we're doing the calculation. So that's a fairly vague description to these things, but just remember it's where we do the inputting. It's the input part. And sometimes it can be quite simple and other times it can get kind of complicated. When it's complicated, we use parentheses to keep it intact. And we're going to be talking about logarithms and we're going to be talking about their arguments. So that is why John wanted to take a minute to clarify what that word means. Okay, I'm going to flip the page because I'm going to start making a chart that is going to be our friend forevermore. You guys are familiar with my good friend, the rules of exponents chart. Well, I don't know if Laura and Vivian are, because this isn't something that's in the book. This is my little friend that I made up to help us keep all this straight. Draw with me. We've been talking about rules for exponents for a long time. And hopefully you've memorized them. They are the product rule, and they are the quotient rule, and then we have the power rule. Okay? And we use this little shorthand to say if we're multiplying matching bases and they have exponents, we can simplify by just adding the two exponents. And the quotient rule, and product implies multiplication, and that's when we're multiplying. The bases have to match. That's important too. If we're dividing matching bases that have exponents on them, we can simplify by subtracting the exponents, the numerator minus the denominator. And then the power rule says if we've got a base that's being raised to a power, this is an m, then we multiply the two exponents. All right? This we know, this we've been working on since Algebra 1 days. Laura and Vivian, you might not have seen it in this chart format, but you've seen this notation before. We know that exponents and logarithms are the very same idea. They're conceptually exactly the same. We format the problems a little differently and we attack the calculations slightly differently, but exponents and logs really work exactly the same way. So we're going to explore, and we did this last year too, what we're calling laws of logarithms. And what we'll see is that they parallel exactly to the rules for exponents. Now, I always think that exponents got a bad shake on this because would you rather be a rule or a law? I think this sounds way more lofty and cool. But what we're going to see is that when we compare the product law for logarithms, it's going to look a whole lot like this. So let me show you how we write this. Okay, what this tells us is that when we are adding logarithms on the same base, we can multiply the arguments to simplify them. Technically, don't worry too much about trying to find this exact expression in here, because you know how it is, exponents going into logarithms, it all goes a little sideways. But the concept is the same. If you're multiplying in the argument, you can also consider them as added separately, okay? So this relates to that, and when we use it, you'll see how that works. And then we're gonna go on and fill this in. Let's just do it now. Let's fill the chart in now. John goes step by step. If we have a logarithmic expression with division in the argument, we can change that into a subtraction problem. Okay, so division and subtraction correlate, just like multiplication and addition correlate. And now this last one seems really random, but it's super useful. If we have an argument that's being raised to a power, we can take that power and basically jump it down as a variable in the front. That's weird. That doesn't really look like this, but it works it works in the same kind of instances. So we're gonna do some problems today to illustrate each of these, and one of the things I want you to take away right from the beginning is just like here, but really even more so, we can go in either direction. And we do go in either direction on these. So we can use them however we want to simplify, going in other directions. Let's try a couple examples. Please make sure this gets written in your book. Let's work on them first, and then you can go back at the end of the lesson and add them, because I want you to feel a little more comfortable about them before you write them down. Okay, here we go. Log B4 plus log B6 equals log quantity x plus 4. Okay? These are the arguments, just so you know. Whoops. These little b's just help us to remember that these are all the same base, right? And that's cool. That means any of these rules can apply. So what happens here is we see, oh, look, we're adding 2 logs. How can we simplify that? Oh, we can multiply the arguments and write them as 1. So we can rewrite all of this as log B24. So we just used the first law of logarithms to simplify this, and it equals log b x plus 4. Now, you may remember from our logarithms work that if the logarithms are the same and the bases are the same, then the arguments must be the same too. So if these two are equal to each other, then we can just pop off the arguments and solve them. Isn't that so cool? So then we subtract 4, right, to isolate the x, and we get x equals 20. And the last thing that we have to do for a log problem is that the argument must always be positive. The argument in a log must be positive. So it's always a good practice just to stop and check that it makes sense. This is the correct answer. Okay, so there's a problem illustrating how we can use the product rule. Let's go on, and I bet you'll never guess what's going to happen in the next one. You'll never guess which rule we're going to use. 40.2. Log we put parentheses around the argument when it's complicated. We don't have to put parentheses around a simple argument like that. All right, again, we notice that the bases are all the same. That's good, we can ignore them. We can see that the way this problem is set up, it's designed to help us practice simplification and using the laws of logarithms, so we're not gonna have to use our calculators to resolve anything. All right, so we see subtraction, and we know that if we're subtracting two arguments, we can combine them through division. So we can say the log 4 of x plus 6 over x minus 1 equals log 4 of 5. Okay, so this subtraction allows us to divide the arguments. And the reason why that's so useful is because once we get both sides into a single log expression, that's when we can pop the arguments off and solve them by themselves, right? In this phase, we can't pop them off because this side is two expressions. We have to squish it into one before we can pop the arguments off. But the second law of logarithms allows us to squish, and then we can pull them off. All right, so now we're just going to cross multiply, and we get x plus 6 equals, I'm going to distribute as I multiply. It'll be 5x minus 5. Allow me to add 5 to both sides and subtract that x. And we shall get that cancels, 11 equals 4x, divide by 4, and we get x equals 11 over 4. Yay, positive number. All right. Last one we're going to use twice. Solve 3 log bx equals log b8. Okay, again, we have matching bases, so we can kind of ignore that. We just need to squish both sides so that we can pop the arguments off. However, this coefficient gives us drama. We can't take the arguments off to solve until this becomes part of the argument. So we use our power law, which tells us we can always pop that back up as an exponent. So we can rewrite this as log b x to the 3 equals log b8. Now our arguments are nice and clean, so we can pop them off. X to the 3rd power equals 8. We take the cube root of both, and we get x equals 2. Yay, this one's right also. Okay? Once you use these rules and you understand that these problems are just an exercise in learning to use the rules to clean up the arguments so that we can pop them off and solve them, no drama, right? Last one in this category. Yeah, we have another topic. I'm sorry. All right. Log 12 x equals 2/3 log 12 64, sorry. I was looking at the problem and the answer interchangeably, and I could not figure out why I was seeing such different things. Well, it's quite simple, isn't it? All right, again, we notice that the bases match, right? That is good. It doesn't matter if they're letters or numbers, you guys. As long as they match, then we know we can proceed using the laws of logarithms. The laws of logarithms only work when the bases match. So we just notice that, and we don't let it throw us off that it's a big crazy number or it's a letter. It doesn't matter as long as it's the same. And as far as I know, John never creates any drama with that. Okay, again, we have the same problem as last time where we've got this coefficient over here. In order to pull the arguments, we can't have a coefficient, so we need to take this and pop it up there. Now we can say log 12x equals log 12, sorry, I was going to try and write it big, 64 to the 2/3. And that probably starts to make your heart beat a little fast because what the heck, fractional exponents, that's a whole nother can of worms, isn't it? But don't worry. We now have nice, clean arguments, right? One on each side. So we can say x equals 64 to the 2/3. All right. Now, how do we do that? Remember that the way we want to break this down is to say it's 64. First, we find the root, and then we'll expand it, right? We take the denominator first to make it smaller, and then we'll use the numerator to make it bigger. What is the cube root of 64? Three numbers that multiply together to give us 64. Oh, that's 4, right? So the cube root of 64 is 4. Then we square that, and so our final answer is 16. Yay! The laws of logarithms are our friends, all right? New topic. And there are two problems with this. Okay, this isn't difficult, but at first, and especially coming after all that we just did, this might feel a little mind-blowy. This is section C, and it's about inverse functions. Remember, inverse functions are where we start with an input called A, we put it through some sort of function, and we get a product of B. The inverse function allows us to take B, put it through, we're calling it the inverse function, and this time we'll get out A. Okay, so these guys have an interesting relationship, and we're going to explore a little bit about what that looks like. If we call this one the f of x, and we call this one the g of x, then we should be able to take, this looks really weird. We should be able to basically plug them into each other and get out the same answer. So let's take a look at a problem that shows us what this looks like. It's not that hard. It sounds really confusing, but when you see the way the numbers behave, it will be much better. Okay, the f of x equals 1/3 x minus 3, and the g of x equals 3x plus 9. So what we want to do is we want to show that this is true. So the first thing that we'll do is calculate the f g of x. How do we do that? Well, we want to take the g function, this value, and we want to plug it into f, right? So first, I just substitute the g function in right there. Now we're going to take this and put it into the x function, so that will be 1/3, right? And now for x, we'll put this in, 1/3, 3x plus 9 minus 3. Okay? Now we just have to do the algebra. Just a second. I'm confusing myself. No, we're good. We're good, we're good, we're good. Okay? So now let's just simplify this. This is a denominator of 3, so that becomes 1 plus 3, 1x, right? 3 over 3. This 1/3 times 3 simplifies to 1, and that leaves just the x. Now I distribute the 1/3 against the 9 and get 3 minus 3. Oh, look, those two cancel each other. So we got x, just like we were supposed to. Okay? So this one checks out. Now we have to check this one and see if we get x as well. So I'm going to do it over here so I don't have to turn my page. This time we're going to take the g function and we're going to solve it for the x. Okay, so that's what I want to do. There's my g function, so it's going to be 3 times 1/3 x minus 3 plus 9. See how I'm doing that? It's kind of mind-bendy at first, but it's quite simple. You're just plugging one function into the other. And now we just need to simplify this. I distribute the 3, that becomes 3 over 3, so that's 1, so it's x. And this becomes 3 times minus 3, that's minus 9. Plus 9, we get x again. So this one checks out also, and let's see, John said to show that these are inverse functions by computing their compositions. So that's what this is called. Computing compositions of the functions. Wow, that sounds really smart, doesn't it? And the way that we compute the compositions is by doing this calculation. Okay, let's do one more. The only thing that's difficult in these is keeping your head straight as you plug them into each other, and then solving. Sometimes the solving gets a little crazy. These solved pretty neatly. The next one's going to take a little bit more work, but that's our last problem. Example 40.6. Show that f of x equals 1 over x minus 3. It's getting dark outside today. My eyeballs are starting to go. And then g of x equals 3x plus 1 over x. Okay, so the first thing we're going to do is we're going to take the f function and we're going to put the g inside of it. So that will be taking this 1 over, and then this goes where the x is. So that'll be 3x plus 1 over 1, over 1 minus 3. Right? And we take a minute and just breathe and make sure we got that right. Yeah, the f function is kind of the outer shell. And then here where the x lives, that's where we put g in. All right. I'm just looking to make sure that I copied things correctly. And this is not right. It should be over x. 3x plus 1 over x. I knew something didn't look right. Yes, okay, now we're right. I copied this one wrong. All right, so now our work is to work on complex fraction stuff. So we need to get these guys together. He needs an x in his denominator so they can match. This will become 3x plus 1 minus 3x, and everything's over x. This cancels out, and we get 1 over x, so I'm going to multiply it by x over 1. That will cancel the 1s and cancel the x's. I'm good. Now I just have to multiply the top by x over 1. 1 times x over 1 equals x. So we did it. This one checked out. All right, that was cool. And how fun is it that we were able to use our complex fraction knowledge and have it cancel in such a satisfying way? That's what's fun about these problems, you guys, is that they're all about the canceling. Okay, so this one worked out. Now we're going to do the g of f of x. So this time, the g function is going to be the outer shell, and we're going to plug the f function in, ooh, not once, but twice. Okay, so let's write the outer shell first. 3, and there will be the f function plus 1 over the f function again. The f function is 1 over x minus 3. Okay? G on the outside, f on the inside. That's what we want to do. Now we have to simplify all of this. Are you ready? Okay, let's get everything with matching denominators and all cleaned up before we start trying to eliminate that. So this will become, distribute that, so that's 3 over x minus 3 plus, and then let's give this the same denominator. So then we can simplify this to, oh look, it'll be 3 plus x minus 3, so that'll just be x over x minus 3. All right, so that's our numerator simplified. We changed the denominator on the 1 to get it to match. Then we squished it together. We actually added it, and we had 3 plus x minus 3. So the 3's cancel, and we're just left with this in the numerator. Now let's do the denominator. Oh, well, it's just 1 over x minus 3. So we multiply it by its reciprocal, x minus 3 over 1 times x minus 3 over 1. This all cancels. These cancel, and look what we're left with, x. So these we were asked to show again, and that's what we proved. Because we proved that the f of the g of x equaled x, and the g of the f of x equaled x. If we can prove both of those things, then we prove that they are inverse functions, and we proved it by, again, the phrase is computing their compositions. That is a very specific jargony phrase, but I want you to have it in your head, because somewhere along the line you're going to run into another math teacher who will assume you know how to compute the comparison. And you do know, and now you'll remember that you know. Okay, lesson 40 is done. Whew, that was a workout. These have been a tough couple of lessons, you guys, and I really admire your willingness to stick with me, especially in video format. It's hard, but you're doing a really, really great job with some tough material, and you are amazing. I will talk to you soon. Goodbye.